Okay, welcome everybody. I'm happy to see so many faces. I think this is because of our speaker today, and I'm really pleased and happy to welcome Rupert Klein from the University of Berlin. And before starting, let me make some comments on his interesting vita. Rupert Klein started studying mechanical engineering in Aachen. So, first of all, was an engineer, which turned into kind of mathematician, I would say. And he did his PhD and also his habilitation with Norbert Peters at Aachen. He did a postdoc in the Kuran Institute with Andy Myler. Then his first professorship was in Wuppertal. I think not everybody is familiar with this city. And shortly after that, he went to Berlin. He held a joint position at the PIC, the Potsdam Institute for Climate Research, and at the same time at the Freie University in Berlin. And now he gave up the position at PIC, and he's now at the Freie University in Berlin. He declined a couple of offers from very prestigious places like ETH in Zurich, Johns Hopkins, and even Princeton. Your comment then was kind of boring. So Berlin that time was more exciting in terms of applied math. So Rupert is also a member of the Berlin Brandenburg Academy, and in 2003 he was rewarded with the highest German research prize, the Leibniz Prize. And today, I mean, his field of interest was started with combustion, and then he turned to meteorology and climatology. But well, then it's inevitable that they come across, say, with machine learning. And today, he would like to share some critical view on the current state of machine learning. May I say so? So, the stage is yours, and we are very much looking forward to it.
Thanks, Enrique and Rupert, for hospitality, for inviting me, giving me the opportunity to speak. I'm not a developer of machine learning techniques. I'm not even a user of machine learning techniques, but I've seen in my circles in applied math that more and more people are jumping on the train and start using this machinery for all sorts of purposes. And some of this has been bugging me. And at some point, I thought I should collect my thoughts, and whoever doesn't run away when I start talking, I will let them know what I think about this stuff. And now you're my victims. I will report specifically on results from John Siegel, Junkai Li, and Jin-Chao Xu. Some of you might know Jin-Chao. He has made his career in, of course, the numerical methods for PDEs. He has quite a name there, but has recently done some work with these postdoc and PhD student that I will refer back to. And the second group I will mention prominently is Ilya Horenko, who is now at the Technical University of Kaiserslautern-Landau as a professor for artificial intelligence, and a team of postdocs and cooperation partners in bioinformatics, and this is Susanne Gerber, and in climate research. That's I'm Terry O'Kane. I didn't even mention it. Anyway, okay. So without further ado, I try to get this thing going. Yes. The motivation behind what I'm talking about is from my area of research, atmospheric and ocean flows, and it is about the story of El Niño prediction. El Niño is this phenomenon where in the Eastern Pacific, the sea surface temperatures rise strongly around Christmas time, and then the phenomenon holds on for up to 2 years. And when the surface is so warm, it has profound effects on the atmosphere, evolution of the atmosphere in the region. And it's so drastic that farmers, in particular in southern South America, they would like to know as long as possible ahead of time whether an El Nino is coming or not, because it would help them dramatically to buy the right crop seeds in order to basically cover and counteract the adverse effects of the El Nino. But economically, incredibly important phenomenon too, because of these what is called teleconnections. The rather wet and cool 2 years we've had around our area here have to do with the presence of an El Nino in this region. And when the phases change, we will see other weather patterns again over here. So it's actually a global phenomenon. And it turns out that physics-based models like weather prediction or climate models have a very hard time predicting accurately for the following reason. Weather models, weather forecast models are fine-tuned to make as good as a prediction as possible for a couple of days. And it is known, even theoretically, that beyond 10 days, the weather develops its chaotic behavior and the trajectories depart, and a precise weather prediction isn't possible anymore, which is why these models are not designed to do more than 10 days. So if you want to go a couple of months ahead, obviously these models will be suboptimal for the purpose. In turn, climate models are made to simulate the statistics of climate, and the definition of climate is the statistics of the weather over something like 30 years. So you don't get an answer from a climate model for what happens 2 months ahead. If you run it for 30 years, real time, then you get the statistics of what happens in the 30 years, but you don't get any accurate information of what happened when, except for maybe within a season. And this is why neither the physics-based weather nor the physics-based climate models are good at doing this kind of seasonal, interseasonal, few-year predictions. And that was a motivation for Ham and colleagues to work out a neural network-based, machine learning-based tool, and published in 2019 in Nature. And what they achieved was to go considerably beyond the 10 months of reasonable, valuable prediction that you can get physics-based to 16 months accuracy from data. How did they do that? Basically, you have to know that over the past 60 years, weather services have been recording all the observational data they have been using to do the weather forecasting, and it's all still available. And now what is called a reanalysis nowadays is you take all these data from back then, you take the best available weather forecasting scheme, and you run it forward through the decades using data assimilation machinery to basically steer the run as close as possible by the observational record that you have had. This is the best reconstructions of what happened in the atmosphere in 3 dimensions that we can nowadays come up with. And Ham and I used these data from the 3-dimensional evolution of the atmosphere from the reanalysis, and of course the observations of when did an El Nino occur back then, to basically train a neural network to say, I give you the data from, say, 1965, and I want to know from you, does an El Nino occur 60 months later or not? And that was their classification scheme that they tried to train the network for, to say El Nino, yes or no, given conditions sometime earlier. Okay, this is the background. And then my colleagues, Ilya Orenko and friends, they used, just as Hamed Al did, sea surface temperatures, but they also used, on the suggestion of Terry O'Kane, the vertical slice along the equator of ocean reanalysis that Terry had available, because he was interested in the question, does the vertical distribution of temperatures and etc. in the ocean near the equator, does it also have an influence on El Niño evolution? And if we knew this well, would it give us predictive skill? That was his science question behind including these data. So they looked at this vertical gradient of temperature in the slice and the sea surface temperature over here. And of all these fields, Terry had available the empirical orthogonal functions of the first couple hundred of them of these distributions. Principal component analysis, empirical orthogonal functions, Carhoon and Loewe decomposition, it's all the same thing. So if one of you hasn't heard one of the notions, the other they might have heard. It's basically trying to find out the statistically most important spatial modes that, as one says, explain X% of the statistics over the period. Okay, this is the data they took, and it's in total 200 degrees of freedom. They took the most important 100 degrees of empirical orthogonal function amplitudes for these two fields. And then obviously they had the El Niño index, which is 0 or 1, depending on El Niño was there or not. And so this, what they actually wanted to learn is a function that goes from R200 to R1. Constraint is that the number here has to be between 0 and 1, ideally only 0 or 1, but that's not what one aims for. One tries to do a probability statement. And the 200 degrees of freedom are mapped to the probability that the El Niño index, as the meteorologists call it, is 1 or 0. And the probability, the El Niño index, that's sort of interesting also, just from to learn a bit more about the concept. One takes the long-term average, 30-year average of sea surface temperatures in the region, and then compares that with the 5-month average in this region. And when the deviation between the two is bigger in modulus than 0.4 degrees Celsius, then it's either El Niño or La Niña. When it's hotter, it's El Niño. When it's colder, it's La Niña. And if it's in between this window of plus or minus 0.4 degrees, it's just normal, nothing.
But in reality, it's very clear whether you have El Niño or not.
Really?
In reality, it's clear whether there's El Niño or not.
It's this is the definition they give.
Oh.
That's all I can say. Yeah. Yeah, and they have good reasons to say it's essentially the same phenomenon, although it varies in amplitude and so on and so forth. Anyway, that's the framework. And now let me dive into. I hope there's more space up here. If you can't read the formulas, please don't hesitate to come up front. Remarks on high dimensions. So suppose we did, for simplicity, just 100 degrees of freedom of an input to the function we want to learn. And we take the measurements of these 100 degrees of freedom every 6 hours over 30 years, roughly half of the data which they were training their neural network or Elias machinery with. Then how many data points would we have? It comes out as for 5 million. Individual amplitudes of empirical orthogonal functions. It's 100 degrees of freedoms, 4 times a day, 365 days a year, and 30 years. Okay, now we want to learn a function, as I said before, from here. It's 100 degrees of freedom, R100 into R. Think of the simplest possible function I can think of that's non-trivial in n dimensions. It would be the multilinear function on a unit cube, just for a concrete example. Right? Bilinear on a square, trilinear in 3 dimensions, etc. How many degrees of freedom would we need to nail and numbers to give in order to uniquely fix the multilinear function on the 100-dimensional unit cube turns out to be 10 to the 30. Let that sink in. This is 10 to the 25 more than we have data points here. It's completely out of the question. And it's pushed under the rug all the time. We will not be able to learn a non-trivial function in 200 or 100 dimensions that really exploits the degrees of freedom it has in 100 dimensions. We cannot even store these degrees of freedom for the simplest multilinear function on any computer we have today. Doesn't fit, not to speak of doing anything with these data. So therefore, we will not learn a function in 100 dimensions, period. No matter what the machine learning tool is we have. Impossible. So therefore, since we know that machine learning works on many problems and it gives astounding results, the only conclusion that we have is behind the scenes and without us seeing it explicitly, there has to be a drastic and systematic dimension reduction, or the effective function we are learning is rather in something like 10 or 20 dimensions, but not in 100. And if this function we want to learn must have this redundancy, and then at the same time, if we're serious about using this machinery in science or for safety relevant applications, then we better know how our machine learning tool recognized that there is this dimension reduction and how it achieved it. And in the end, we would like to control that it actually picked the right dimensions and didn't miss any, and so on and so forth. These things are never much discussed when you hear people talk about how great neural network learning is. But that's behind the scene, and I'm very dissatisfied with how things are presented most of the talks I see. But there's more. There's a couple of open issues, and I know some of them are being worked on very intensely by some research groups, and maybe this isn't totally up to date anymore, but let me go through the list and give you some things that are also critical in this context. The first is interpretability, explainable AI. I don't say much about it. This notion is in the science community now. People are aware that it's really important and people are working on it, but there is no satisfactory solution to my knowledge that would make it really explainable in the sense of we understand what this piece was doing. Then the first thing in analysis we teach our students when we introduce functions is that a function has a domain. And it has a range, and then it has a map from the domain to the range. And why is the domain so important? It's so important because only within the domain are you allowed to apply the map. Outside of that, no guarantee for anything. Does any of the neural network technologies give you seriously a measure of what's the domain of the function it has returned? I don't think so. Very bad. For mathematicians, we should be jumping up and down and saying, what? You're telling me you're learning a function and cannot tell me the domain? That's not what you're doing. I find that a serious issue. And I believe it has to do with the fact that these adversarial attacks, where you basically paste a little black square onto a stop sign, and the network doesn't recognize the stop sign anymore. This kind of issue has to do with this fact. Because in the high dimensions, you have these planes that are created by the networks. Maybe I'm talking too much off my slide. I can get back to this. So I think it has to do with this adversarial attacks. That the domain of the function isn't known generally. Then they are very data greedy. You need a lot of data to train them. Really a lot. Then the parameter estimation problem is really hard. I had seen Stephen Wright give a lecture at our Berlin Mathematical School. Stephen Wright is an an expert, world-known expert in optimization. And he basically said, talking about neural network training, that basically he had thrown the towel and he said, we cannot do better than stochastic gradient descent. That, however, is at most first order in terms of convergence rates and typically slower. And that's extremely expensive when you think about what in the usual field of our business of finding zeros of functions, the Newton method, for example, could be. We all know how much more efficient this becomes. And it's not for nothing that Sam Altman is asking for a budget for computers for AI training that's basically larger than the military budget of the US. It has to do with efficiency. Then, yes, there is an issue in high dimensions and with functions that have local support of one behavior of the map, and then in a different local region, it has a different map, basically, which is easily probable that you have a switch in between at some boundary, and then it's a completely different function. Why is that an issue? Well, this is where He et al., Junkai He and Jinchao Xu came in, and they did ask the following question. Suppose we take a ReLO DNN. This is these neural networks that use as numerals these ramp functions. For x less than 0, it's 0. For x larger than 0, it's x. So it's a ramp function. And the network gets the projection of the input vector, the 100 degrees of freedom or 200, onto a parameterized vector in the same dimension. And the scalar that comes out is put into this ramp function, and that's the output of the neuron. Okay? And so it's known that when you use these rectified linear unit switch functions, then the result of will be a function that is linear on polygons. It's piecewise linear function, it's continuous, and it's linear on polygons in the high dimensional space. So they asked, then we should be able to do the simple most piecewise linear function that we can think of, namely the finite element basis function. Can we do that with a ReLO DNN? And then can we do it in 1D and higher dimensions? And in particular, how many parameters of the ReLO network do we need in order to do this in high dimensions? Result, yes, you can. They showed an explicit construction, number one. Number two, their estimate of how many degrees of freedom you actually need is of this order of magnitude, and that's sharp. You can't get away with less. They used found out the optimal depth, and then found out how many degrees of freedom, how many neurons do you need. And the result is, if the dimension of the space is capital D, then the number of degrees of freedom you need to have an n-node simplex grid with piecewise linear functions on them goes like the dimension times a number that's bigger than 2 to the power d. So the curse of dimensionality hits you square in the face, and there's no way around it if you want to localize those functions. In contrast, when you do this with finite element square, then you just have d plus 1 times n. Okay. So this is extremely inefficient in terms of over-parameterization. You need to throw parameters over parameters in order to do this localization, and you haven't gained anything, because you could do the same thing with just this many. Bad. Okay, now enough of neural network bashing. Let me tell you what my colleague Ilya Horenko suggests instead for this identification, classification of any news. That's the method. It's on one page, this is it. And I'm going to walk you through every detail. And I claim that in the end, you will agree with me that you have understood every ingredient in the formula and what it needs to be and what it is. Let's start. So what we want to do is we want to say a mechanical, yes. Yeah. So there is a functional that we want to minimize. given the data, x is representing our input to the functions. That's the 200 degrees of freedom over many, many time slices. The pi delta t here is the 0 ones for a linear or not, data t later than my latest input. Then we want to find 4 matrices, basically, in the course of minimizing this functional, S, gamma, W, and lambda. And now I'm going to walk you through what those are. The S here is a matrix that has as its columns the coordinates in our high-dimensional space of reference points, as I call them, representative points in the argument space. You could think of them as cluster centers, which Ilya uses as a phrase often. But in the way it's written down, the functional is written down here, it's somewhat different. So it's characteristic points, important points in state space, which you use to do the following. You take a convex combination of these reference points in order to get as close as you can to the data points x, which are the black dots in my sketch. Now, obviously, in 2 space dimensions and with a triangle, you can reach every point inside of the triangle exactly by a convex combination. That's the nature of a simplex. But now think of, we are in more than d+1 dimensions, then obviously these points can point off in the 3rd direction, and then it only becomes an approximation. Okay? So what you want to do is, as a small number of reference points, convex combined with weights that are stored in the matrix gamma, right? So the columns of gamma are the convex combination weights of the columns of S. So you do, by S gamma, you do the convex combinations to move you close to a data point X. This bracket here, squared, is basically looking like the Euclidean norm of the distance between the approximated points and the data points. And for now, let's stick to that. And if you achieve somehow having found a good combination of S and gamma, you have the first dimension reduction achieved, because you don't have to handle all the data points anymore. You have to reduce it to the central points, the reference points, and then approximating new data points by the convex combinations. First dimension reduction has taken place. Now, however, as I explained before, 200 dimensions, the function is not going to be 200 dimensional. If it really is, we cannot learn it. So we have to hope that some of the dimensions are less important than others. The idea here is to say, let's assign a weight WD to each dimension in this sum from the Euclidean norm. So make it a weighted Euclidean norm. And when the WD is small, basically you ignore the error in approximating your point. You do that when the error has no influence on the quality of the result. And when the W's are large, then this is really the important weights, the important directions in your coordinate space. Now, you don't want to lightheartedly throw away dimensions, and that's why you put a penalty for discriminating dimensions, which is the Shannon entropy, minus the Shannon entropy here, of the distribution. The W's are a probability distribution over the dimension. So the Shannon entropy as a penalty does the following. It basically produces the probability distribution that still satisfies basically your minimization and gives a satisfactory result. So that's, you don't lightheartedly discriminate. So that explains the gamma, the S, and the W. And now let me come, yeah?
But this is not in terms of the coordinate system, right?
Of what?
Of the coordinate system.
That is an issue to be discussed. I'll get to that later. But you're right. So at this stage, it's a given coordinate system, and within that coordinate system, you try to find unimportant or important. And there can be problems when you take a given problem and rotate it in some arbitrary fashion, where that technique is going to fall on its nose. But Ilya's next papers down the road, they addressed it, and are addressing it still. Anyway, but that's a good observation. And now let me get to the lambda, That was the last degree of freedom here. Basically, the pi's here, the zeros and ones, you can interpret them as a probability distribution as well for a given point in time, and linear or not. And now what you want is that you want to assign, like in a finite element function, in fact, it turns out to be a finite element function in the end, assign to each reference point, which is now to be thought of as the node of a finite element grid, you assign a value of the probability for that reference point, and you find inside of a simplex, say here, you first find the best convex combination to approach that point from the reference points, and that convex combination, these weights, you use to also combine the lambda values, the functional values on the grid nodes, in order to approximate the probability of appearance. It's just exactly the linear finite element idea. But now we have two probability distributions, exact 0 and 1, and then numbers in between to compare. How do you compare probability distributions? You do that by the Kullback-Leibler divergence, or relative entropy, as it is sometimes called. It's this expression. So basically you have the minus the Shannon entropy of the pi distribution, plus the expected value of your approximated probabilities under the exact probability distribution. It turns out this thing is 0 only if both distributions exactly agree on every entry, and it becomes positive if that isn't the case, and there's also a certain monotonicity in there. The bigger you are away, in some sense, the discrepancy increases. So you want to minimize this expression. Okay, now you have this entire this entire functional, and we have two ways of reducing dimensions. One is introducing the reference weights, the reference points. One is discriminating dimensions. So we get explicitly told how is the dimension reduced in my learning process. And by the convex hull of the entire grid of reference points, here is a different version where you can basically say I introduce more than d plus 1, in this case, reference points, but I introduce a penalty that the reference points should not be too far from each other, so the square distance is not too large. Then you can actually encapsulate nonlinear manifolds in the space, and it naturally, by the convex hull, tells you what's the domain of the function. Great, problem solved. So when now somebody gives me a data point out here, I can still evaluate possibly my function if I were to extrapolate, but I wouldn't, because I know I'm outside of the domain where the data has justifiably given me a function. So this method does that part automatically that I've been advocating for. It gives us a domain of the learned function. Now, when the dimension is higher, then think of the third dimension being the many other dimensions. Then all of these expressions do not become 0 exactly anymore. They're only an approximation, but the whole gist of the approach still holds. You're building something around the data points, which is typically a very low dimensional something in your high dimensional space, right? Because you have only 5 million points in that many dimensions. And then this encapsulates that. And you get told what's your manifold and what's the domain of your function that you have learned. Now you could say, but this functional is a mess. In fact, it is non-convex and every bad property that you can think of, more or less, of an optimization problem. But then Ilya has been trained in numerical mathematics by Eberhard, and so he thinks about this question also from the numerics point of view. And what you see when you stare at this for sufficiently long time, you see that if you introduce an iteration procedure in which you freeze 3 of the degrees of freedom, 3 of these matrices, and solve for the last one, then 3 of these problems can boil down to available analytical solutions. So you just program them, that's it. No more work to be done. And the last one that has to do with the Kullback-Leibler and the logarithm having the gamma and the lambda in here is still a convex optimization problem. So there's efficient algorithms at least to get there. If you're willing to make one more step of approximation here and say, let me use Jensen's inequality, meaning that if I have a convex function, I can always be with a linear approximation, I'm always below the convex function. That's basically what Jensen's inequality says. If you're willing to use that here and you replace the last term with this expression, then you know you have an upper estimate of your functional. And if you minimize that, you know the real functional is still below that. So this is often a good approximation. And if you are willing to do that step, then all of the 4 subproblems with 3 frozen, 1 solved for are analytically solvable. And it also turns out that the smoothness of the problem in each frozen subproblem is such that you find the basically it's a smooth minimum. You go there, you stay, and when you do the iterations, it converges like a Newton method. There's no proof yet, but empirically, it basically always does it. So that means we don't have stochastic gradient descent. We have a Newton-like iteration scheme where all the details are coded in explicit solutions. Very, very fast. And it's, in fact, in terms of a complexity estimate, it is the number of time slices that you have times the number of dimensions you have times the number of reference points you are willing to invest. The K doesn't appear here. No, I wrote that in the matrices. That's the number of reference points. And that's exactly comparable to the most prominent clustering algorithm, the K-means algorithm, which, however, doesn't do much more than clustering the data and nothing else. So it is as efficient as the cheapest machine learning tool that, however, is not a very versatile one. And, well, now suppose you have WS and lambda all learned, then you throw the gammas away because those gammas you learned in the course were only representing your data points or in the training set. And now you give me a new point, x nu. You find by, again, as an analytically solvable problem, the best linear combination weight that allows you to approximate the new x point. This gives you the gamma weights, which you put on top of the lambdas as a convex combination, and that gives you the new prediction for the probability of any new occurrence. Just like you evaluate a finite element function on a simplex curve. You're not happy?
Yes.
Yeah, okay, good. And this is how you use this in practice once you have learned the parameters. Now, this is the method. I explained a few of the degrees of freedom. I think I explained every single piece of the formula. And now let me show you some results. This is on this El Niño prediction problem. What we see here is model complexity, which is the number of tunable parameters you put in, which is basically the number of reference points in Ilias methods, and it's the number of parameters of the neural network in total that you would invest. And on this axis, you have what is called the area under curve. It's a mean prediction quality. So how well does my trained method reproduce the test data set? But in the following sense as a mean, when you go back, I have not mentioned it yet, but now I do. There's an epsilon W in front of the Shannon entropy here and an epsilon lambda in front of the Kullback-Leibler over here. Those are free parameters that, well, we have no argument as yet of how to choose them. This happens in neural networks all the time as well, and there's the established procedure of how to measure the robustness of this approach with respect to the to the arbitrary parameters. And what you do is you take a reasonable range of these parameters, train your network for the different values, measure the error that your function makes relative to the test data, and then you average over that error and make it dimensions. If you have a number of 1.0, your approximation doesn't depend on the parameters at all, and you always hit accurately the function that you were aiming for, or the data points in the test set. Exactly, but that's unrealistic. So the closer you are to 1, the better. 0.5 is the limit where you have learned nothing. You're as wrong as often as you're right, and basically it is meaningless. So therefore, when you have an AUC that is in the range of 0.8, up here, that's pretty good. That's actually, in practice of machine learning, that's a good number, respectable number for a tough problem. And here compared here, a whole range of methods you have implemented in MATLAB. So he uses the neural network technology that he can get there, or other methods like the support vector machine, or a k-means plus neural network, and other methods. He uses them from MATLAB because he can say, I cannot follow possibly every paper that comes out of these methods and use the latest of the latest. I rely on MATLAB and MathWorks to implement proven technology and give me a good code for it. So he uses that and compares with that. And so he has three contenders that are up to the ESPA, entropy optimal sparse probabilistic approximation, which is what I just told you about. And the plus sign here stands for Jensenifying the last term. Right? That's giving you extra efficiency gain. Okay, so there's no, it's not in the support vector machine, sparse generalized linear model, the best neural network contender is the dashed line here that was in the game, and the ESPA method have comparable AUC on this test. When you look at efficiency, this is again model complexity versus the computational cost for the training. What you find out is that the three other contenders are up here at on a laptop at 10 to 1,000 seconds compute time, and Ilya's methods are down at between 10 to the -1 and 10 to the -2 seconds of training. So that's a factor of about 1,000 here. And when you go to higher dimensions, it turns out on problems where something can be learned, the discrepancies become ever big. And that's due to the Newton property of the scheme, very simple. So it's very efficient, and in formal accuracy, it is actually comparable to neural network contenders. And here is a picture that's very qualitative, but it shows the dark line here is when El Nino occurred, or there was no El Nino. You can see here that the green deep neural network approximation shoots off quite a number of times in the no El Nino time intervals, and signals there would be one. And the ESPA plus method is more robust in that sense, but that's a qualitative measure. It was just shown to show that it does what you expect it to do, the ESPA plus. Here is an interesting one, namely it's versus the number of degrees of freedom. So the first 100 is the surface water temperatures. The second to 100 is the deep slice temperature, vertical temperature gradient degrees of freedom. And you can see that only about 15 or 16 of them have a value of the feature weights, WD, that discriminate unimportant stuff, right, that are beyond 0.01. And this means now we found the important dimensions for predicting El Nino in the setting, if you are willing to go after the empirical orthogonal functions. And Ilya actually did that. He threw away all the other degrees of freedom, trained it again with 16 or 20 leftovers that have the high weights, and he basically got the same result. And now you know, How did it achieve the dimension reduction? Through the optimization procedure of everything together, through the iteration procedure. And secondly, it tells you these are the patterns, the spatial patterns that you need to look at if you want to understand NU, and why the ocean does that in the future and why it doesn't do something else. So Terry O'Kane was jumping up and down and said, now I have an idea of what to look at to understand this phenomenon. And no, a neural network would not give you that information. It wouldn't tell you how it reduces the dimensions. It wouldn't tell you what are the degrees of freedom it has kept. It's not there. Okay, last example. This is the so-called Swiss roll example, where basically you take blue dots and red dots and spiral them up. And now you give these data to a machine learning classification scheme, and you throw in any point in the plane, and it should tell you, is this likely a red or a blue point? And turns out that if you take two turns of the spiral, the neural network and the best Bayesian random forest, there's another machine learning tool that they used here, they basically get the same AUC. This is actually 1, this is 0.98, and the ESPA method is also 1. So they do well in 2 turns. But if you take the same number of free parameters of the neural network and you do 4 turns of the spiral, basically the quality of the contenders goes down, whereas for the EDAS method, it stays up. There's a little twist here, which is interesting. When you do the Jensen trick, turns out that the optimization problem can be shown to not give you the edges of the simplices anymore, but it gives you the centers of the Voronoi cells. And then you have a piecewise constant approximation, as you can see it here. It's either blue or yellow, and yellow, no, yeah, it's one color or the other, and this basically is a 0-1 switch. That is a side issue. And with that, let me not bore you with that. I get to the take-home messages. So we are typically dealing with small data problems and not big data problems in geosciences and fluid mechanics and whatever. It's 5 million versus 10 to the 30, as I told you before, right? It's all small data problems. And popular deep learning techniques and statistical concepts might not be the best in high dimensions. That was the work by He and Xu and Siegel and Xu. And then I think, due to the fact that we always have small data, one should not, when doing theory, view this the whole machine learning approach as a statistics problem, but rather as a function approximation problem, which I think many people have understood by now. I hear also including in-house, and Gita Coutinho is working on that in Munich. So it's actually a function approximation problem. I think that that's important, that one doesn't fool oneself when one has statistics when there's 5 million points. It is always, you have to make it dimensionless with what you're missing, what's the space, the size of the space. Then this is folklore and is known to machine learners, I learned a lot when working out this lecture. Information theory is an amazing tool that has a lot of intuitive content in this framework of learning something. And I found what I learned, I found it exciting, and so I'm recommending who doesn't know about information theory yet should take a book and read about it. And the last one, if you take your final problem seriously and you try to apply the knowledge of numerical mathematics to the optimization problems, you can often gain dramatic failures. As the past decades have shown, American mathematic techniques have brought more speed up in practical problems than the speed up we got by faster machines. That has been shown over and over and over again, and this is another great example of that. All right, this was it. I have a couple of references that summarize what I just talked about for you. If you want to have the slides, I can provide them. Thank you very much for your attention.